Hello everyone, welcome to my channel. Today I'll teach you one of the best and most impressive tricks I've ever seen on Euclid's algorithm and in number theory in general. I think this trick is very instructive, and I think it will help you a lot to understand Euclid's algorithm a bit better, as well as to generally improve your knowledge of understanding how to solve problems. So I think that watching this video for you for the next what, 20 minutes maybe, or 15 minutes, not a long time, will be one of the best investments you can actually make. And just subscribing to the channel and looking through other videos, I think I have one of the best content explained in my channel, and I really recommend you to watch through my videos because it will help you a lot to improve. I'm confident. So yeah, I'll stop talking and trying to promote my channel because you guys click off after first 30 seconds, and that lowers my views, not views, but at least it makes me sad. But yeah, hopefully most of you guys stayed, and I'll won't take any more of your time. So here's the problem. This problem is from RMM 2018, problem 4, very serious competition. So yeah, let's go. We have ABCD be positive integers such that AD is not equal to BC and GCD of ABCD is 1. And we take a set S of values that are obtained by taking GCD of n plus b and cn plus d, where n runs through all positive integers from 1 to 2, 3, 4, blah, 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 so on. We want to show that set S is a set of positive divisors of some other integer. That's the problem. Okay. In another video, I talked about mind maps, and here we'll make a quick one, just not to bother, because there's not really much to discuss. You can go about it in a more complicated way, in a more like number theoretical way. You can but kind of like what I want to show is more of a tricky way to avoid like doing a lot of work. So here's our mind map. Okay, we have a mind map. So we have a problem. We have a problem, and we want to find a proof. How do we do that? So essentially, you take a problem statement, and then we want to understand, do we like it? Do we not like it? And essentially, when we have a problem, you always want to look at the problem statement, and problem statement has a set of conditions. So uh, we take a look at a particular uh, condition. For example, here it's like ABCD is equal to 1, or a condition can also be something like S is the set of values obtained by GCD of n plus b and cn plus d. And then we ask ourselves like a question, do we like this condition? Can we use it in a good way? Or do we not like it? And we then have a couple of options. So if we don't like it, leave it and use later, rephrase it right now. So again, these two, and there's always two cases. You can always, if you don't like it, if you feel like jumping straight too much ahead, you can leave it and try to use it later. Or you can rephrase the condition and try to use it now. But the end result is always the same, is extracting new information from a condition. So using deduction or reduction doesn't matter, but we want to extract always some new information. And by extracting new information, we kind of go back to this loop of new conditions that we get. And then from there we go to the proof at some point when we gather information. That's like a mind map of any question. So just remember how to structure this thing. And now let's look at what's actually happening. So we have here a GCD of this thing. Do we like this condition? So no, we don't like this condition. The reason is n plus b and cn plus d is very random. And actually, if you think about it, the whole problem just revolves around making this particular condition good, because we don't know anything about it, but we kind of do know that it's a set of positive integers, so it's pretty cringe. So here comes another thing that comes to mind. We have, so what's this problem about? So when you write your mind map, also always consider what methods can you use, what ideas can you use. So for example, if I want to go from a problem statement up in the header and some here proof, then in the middle you want to write down methods, like what methods can you use. So for example, here we can use Euclid's algorithm, and that's like probably the only thing you can use, because yeah, we kind of want to go this way. So we don't like the condition. Do we not like it? We can't leave it because that's the only thing we got. And we want to, so we need to rephrase it. And the only way we can kind of like rephrase GCD is Euclid's algorithm. So yeah, unfortunate, but that's the only option we get here. And actually, Euclid's algorithm gives us quite a neat thing. So first of all, we can go and write down that GCD of n plus b and Cn plus d is the same as GCD, or uh, it divides the GCD. Ooh, that's pretty interesting. The GCD of ANC plus BC and ACN plus AT. The reason why it's pretty obvious is just because we multiply one part by C, the other by A. We can see ANC and ACN balancing out, and we also get this AD minus BC idea that we saw here, which was a bit cringe when we looked at it first, but now it's kind of like cool, and we understand it because GCD of this thing is just GCD of this. And this is always dividing AD minus BC. And we're like, okay, this is pretty cool. Maybe S is always a set of positive divisors of some integer that is AD minus BC. And then you try to test it, and it doesn't work. So actually, it's not the set of positive divisors of AD minus BC. Yeah, stay hydrated, guys. So now, okay, when we look at this, the other way we can use GTD, so that's like maybe the second thought you get, the stupid and most like stupid and both useful thought you can get here is actually just this. And you can say, Michael, what are you talking about? This is so stupid and so silly. This is just like Euclid's algorithm. What does it give us? Well, here comes the trick. Here comes the trick, guys. And the reason why you kind of want to understand this trick, so I'll give a little another side step. You know, I like to do them, but sorry if uh, that makes a bit the solution a bit longer, but I do think it's an important side step. There's a concept called Vieta jumping. And Vieta jumping is basically a method where we look at quadratic equations, for example, yeah, quadratic equations. And essentially, what you want to do in quadratic equations is you always like of shape something like x squared plus kxy minus y squared, blah 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 blah. Like, yeah, two, whatever. They have a lot of solutions, and the idea is something like taking a solution x1, then by taking k1 minus x1, that's like the second solution, and from second solution you get third solution, and you just do these jumps, whatever. So this is called Vieta jumping. So for example, on a chart, that's our whatever we have, our curve. Then basically what you do is you look at this thing, you look at the x coordinate here, then you look at the x coordinate here. This was like point xy, and then you look at point zx that's here, where this is z, and then you go z here, and then you have another number number t, and blah 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 blah. You go on and on and on. Yeah, and essentially this thing, the the main like cool thing about this problem is that it involves a very similar idea. And this idea is that we can rewrite this thing like this. And when I saw this, I was like, wow, this is pretty ingenious. Um, so we do know this, right? And the reason why this is pretty good is because of the next thing. So first of all, let's note that the problem, it kind of only revolves around like arithmetic sequences. So we don't necessarily need the values of A, B, C, D explicitly, just because N plus B and C and plus D are just basically random uh, arithmetic sequences that are also said to intersect essentially or whatever. Because if A, B, C, D were all divisible by some number, it would be pretty bad. So it just adds a bit of randomness in case. But the main cool thing is that since we're just exploring arithmetic sequences, we can do the kind of like a Vieta jumping idea here. So, and the idea is following. Okay, so we want to show that every quadruple ABCD uh, that for every their set S is a set of positive divisors of some number, right? Well, okay. And when you have these kind of conditions, sometimes it's very useful to do the following. So let's call set quadruple ABCD something if their set S is a set of positive divisors. So we kind of like label some of them good, and then we want to show that everything's good. So let's call a quadruple ABCD skibidi if their set S is a set of positive integers. Great. And then the idea is actually so if and then our main like lemma or claim is that if A B C D is a skibidi quadruple, then A minus C, B minus D, C, D is a skibidi quadruple. And so is A plus C, B plus D, C, D. Yeah. Uh, and this is just because of this thing here that we wrote on top, because these two GCDs are equal. Uh, that's pretty amazing. And the reason why it's amazing is because now we can manipulate A minus C, B minus D, C minus D, C, D, A plus C, A plus D, C, D, because sets A, B, C, D, and other two above have the same set of numbers. And the reason why it's cool is actually because if we just look at A and C, right? We went from A and C, and we can go to A minus C, C, and we can go to A plus C, C. But we also can go to like opposite ones. We can go to A and C minus A, and so on. That's allowed. And so essentially, this is just Euclid's algorithm. And essentially, at the end of the Euclid algorithm, you always get something like D0 or 0D, where D is the GD, but we do have D here. So let's just use X. So X0 or 0X, but because of the A plus C and C condition, even if we get X0, essentially you can go from here to XX, because the plus, and then from here go to 0X. So at the end of the day, we can achieve that A is 0. So essentially, we can assume that A is 0. And the reason why that's good is because now the GCD of N plus B, C, N plus D is the same as GCD of B and C, N plus D. So now we just want to show that this GCD is a set of divisors of some integer. Great. So yeah, and that's kind of the main like cool thing about this problem. Uh, and now we simplified the problem a lot. That's like the main trick that I want to show you guys. But now let's try to, fix the rest and do this thing. So first of all, let's say that so we do want to explore the factors of Cn plus D. And a very important moments about this is that if C and D have a common factor, if their GCD is more than one, sorry, I don't usually write GCD. If their GCD is more than one, it's always divisible by something. So that's not really good. So we can assume that if K divides K is equal to the GCD of CD, right? Then we know that K and B are coprime. The reason is because BCD were coprime, A, B, C, D, whatever, and A is zero. So essentially, K and B have to be coprime, so we can divide everything on the our right hand side on K. So then Cn plus D will turn into C over K and plus D over K, and they're coprime. So we can safely assume C, D are coprime. And now if they are coprime, we can kind of use like a Dirichlet kind of thing, but we also have to mix it up with the Chinese ratio. Oh my goodness, Chinese remainder theorem. Oh my goodness. Okay, so um, essentially we want to use the Chinese remainder theorem. So we want so say we want D is okay, not D. Uh, let's say M is a factor of B. We want GCD of B and Cn plus D equals. So first of all, we do want, therefore, for B to divide Cn plus D, and this means uh, for us that Cn is equivalent to minus D mod E, and for this, in order to, since we can basically pick n, we want C and B to be coprime. So we want C, B, C to be coprime. So now let's assume that they're not coprime. If B and C are not coprime and they're both dividing are divisible by y, so suppose y divides B and C, then the GCD of B, so we basically substitute into something like this: B is B prime y, C is C prime y. Well, assuming y is the GCD, and then writing this, we can say that since D is coprime with Y prime, because B, C are prime in general, this is the same as B prime and then C prime Y, C, whatever, C plus Cn plus D. And now we know that since C and B, they share only Y as their common factor, and then B prime is coprime to C. So if B prime is coprime, or or here is it not? Okay, if well B prime is less than B, and so essentially we can go to GCD in the same similar fashion Cn plus D, where B prime decreases. Always should be a positive integer, so at some point this will turn into one. And when it turns into one, when this GCD turns into one, this means that we achieved such a B that B is coprime to C. So that's so not the this GCD. We kind of want B and C to be one, and when we look at this, we get essentially B. Uh, favoring that and like that. So at the end, we can achieve DC, or say B a lot of primes, so n primes Bn, and then Cn, or not n, m, something Bk, and then Cn plus D to B1, or no, not 1, to B K and C to B1. Uh, and yeah, after this, when we can conclude that, we can say that we take uh, n that's equivalent to we take n that is equivalent to minus d over c mod bk, and that's all good. And we do know that this GCD is equal to bk and then cn plus d. So we're just exploring factors of this. And now we take n is minus d over c mod bk, and we take, therefore we essentially get that bk divides cn plus d. So we do achieve that the GCD of this thing is divisible by bk, but now we want to achieve for cn plus d not to be divisible by anything more. So let's rewrite therefore n as bk times some s plus j. And now if we look at cn plus d, it is equal to bk s n, like this, plus nj plus, oh wait, cbks plus cj plus d, and that's the thing. And we know that cj plus d is divisible by bk, and we now want to show that nothing more than bk is divisible by that. So let's separate bk from cn plus d and get cs plus cj, and then obviously we can get cj plus d over n, which is like this. And note that first of all, cj plus d is over bk is a constant, so we get bk times that essentially, and we want therefore for this not to be divisible by anything more that's coprime with b, so with the first original b. But if we look at this thing, cs plus cj plus d over bk, we note that we can choose any s. So for s of our choice. But here we know that c and cj plus d over bk, they are coprime, as d and c, they are prime. Yeah, from way over here. And if they're coprime, then by Dirichlet's theorem, we can assume that this can be a prime that's very, very big, bigger than b, and therefore this is coprime to b. So essentially we get that this is bk times some number p, and then the GCD that we had of b and uh, cn plus d. Now we get that this is just the same as the GCD of bk and bk times p, which is bk, or any number bk that we chose. So yeah, or shall we say b and bk, like this. B and bkp, and this is equal to bk. Yeah. like this. This is the correct way to do this. Yeah, I think that's it. Thank you everyone for joining in and have a good day, good evening, good morning, I don't know. So yeah, thank you everyone. Bye bye.